we'll first have an array A, B, C, D, E, F, G. Well, an array having 7 elements. And at the beginning of the algorithm, we're going to have infinity stored here, indicating that so far we don't really know whether we can reach these nodes as destinations. And we're also going to use another array to keep track of if we are able to reach a particular node, where did we come from? So we want to record the previous node before reaching each of the nodes. This will later help us to construct the actual shortest path from our starting point to any of the nodes. Right, at the beginning, in this question, since we start from node E, so we know that E to E should have a distance of 0. And since E is our starting point, there's no point we record its previous node because it's a starting point. Now, as we can reach E, we will then see which other node can we reach. And now we're going to use the priority queue as we used in Prim's algorithm. From E, I think we have 3 edges. We can go from E to B with a path length of 9. We can go from E to D with a path length of 7, and we can also go from E to G. That's a 6. Now our priority queue has 3 items, and I think what we can do next would be, we are pretty sure that the shortest distance between E and G must be 6. The reason is that E is our starting point, and if G is the destination, we can either go from E to G directly, or we go from E to some other nodes, then to G. But if we go from E to some other nodes, we'll either go from E to D having an edge weight of 7, or E to B having an edge weight of 9. And then if we go from D to G or B to G through some other path, the accumulated path length must be at least 7 or 9. But from E to G directly, they give us 6. So this means that if we want to reach G, this must be the shortest path. We are not sure about other 2, how to reach B, how to reach D, because it is possible that we can go from E to G and then G to D, having an accumulated edge weight smaller than 7. For this particular graph, we know that E to G, G to D this path has an accumulated edge weight of 10, but it is possible that G to D can have a value of, let's say, 0.5. So we're going to have 6.5, which is smaller than 7. That's why each time we can only take the smallest element from the priority queue, and that will give us the shortest distance from the starting point to that particular node. And for the rest of the nodes, we're still not sure, so we're not going to update any of those. Now, since we can reach node G, we'll then find out which other nodes can we reach by going from E to G and then G to other nodes. The first node we may see is we can now go from G to F. And the accumulated edge weight would be the shortest path from E to G, which is 6. Then we have G to F, which is 1. And this tells us that now we find a path to reach node F with accumulated edge weight of 7. And there's another neighbor D, which we don't know how to reach it. And if we take G as a stepping stone, we will get the shortest distance from E to G, that is 6, plus G to D, that's 4. giving us 10. So that's G to D is 10. But clearly, we already have an existing entry in the priority queue telling us that if we want to reach D as a destination, we have another pass which has an accumulated edge weight of 7 that's smaller than 10. So we are not going to update this into our priority queue. Now, this is the first iteration. And in the next iteration, again, we're going to extract a node from the priority queue. And in this case, I think we have two options, both of them giving us accumulated edge weight, or the length of the pass, equals to 7. And in this case, it doesn't matter which one we pick first, because for both of them, I think we are pretty sure that it's not possible we can find another path to go from E through a path to D, giving us total path length smaller than 7. That's not possible. And also, if we go from E to F through a different path, we shouldn't be able to get a value smaller than 7. So it doesn't matter which one we pick first. Maybe we're going to pick G to F in this round. So we're recording the table. Now we can reach node F with accumulated path length equals to 7, and we reach F from node G. G is its previous node. We're still unsure about the rest of the nodes. Now, since we can reach F, we will also consider what other nodes can we reach starting from F. F has a neighbor D, which in our case we have, well, if we go through this path to reach node D, the accumulated path length would be 7 plus 8, giving us 15. But we know that E to B, or we find another path already to reach node D. E to D. We already found another path to reach node D with only 7 as the path length, so we will not do the update. Another destination is node C. If we go from F to C, the edge weight is 5. Then this means that we found a path from E to C, which has a path length of the shortest path to reach F, 7, plus F to C, 5. So 7 plus 5, it gives us 12. Then the smallest element in the priority queue, I think it should be E to D, giving us 7. And we are still not sure about A, B, C. And now, since we know that we can reach node D, we will then try to check if we can go from node D to some other unvisited node. So D connects to A with edge weight of 1, and at 7, it means that now we find a path to reach node A with total path length equals to 8. We also have a path from D to C. In this case, we have 7 plus 2, giving us 9, smaller than the existing entry. And also we have D to B, but D to B, if we go through this path, then we're going to have 10 as the total path length. That's greater than the existing path E to B equals to 9. So there will be no update here. The next step, I think we'll find D to A, giving us the shortest value of 8. And we're still unsure about the other two. And looks like A shouldn't be able to help us to reach any other unvisited node with an even shorter path length. And for the last two iterations, I think we're going to extract these two elements. So we will eventually have, this is 9 coming from E, this is 9 coming from D. And the items we will have at the end of this algorithm, we're going to have 8997076 telling us if each of the nodes is a destination, what would be the shortest path to reach them. And also, if now you ask how to reach a particular node, what is the actual path from E to a particular destination, then we can use the second array here to tell us or to construct the actual path. For example, if you want to find the path from E to A, then you look into A in the array, you find that in order to reach node A, we must come from node D. Then you will try then find D's previous node, which is E. So it tells us that if we want to reach node D, we must come from node E. And when we look at node E, we will find that E is a starting point. So we will have the path constructed in this way. So that's our Djikstra algorithm. We also use a priority queue here, but instead of just recording the edge weight as the priority value, we instead record the path length, which is the edge weight plus the shortest distance to reach a already reached node. But otherwise, it will have the same idea as the Prim's algorithm. And also a reminder here is that if we want to apply Djikstra algorithm, we also want to make sure that all edge weights are non-negative. We may have 0 as valid edge weights, but we shouldn't have any negative edge weights. Right, that's it for this question. And for the last